The next speaker is Vilda Markeviciute, who is working with Rich Kerswell, I guess. I'm from Cambridge, and she's going to be speaking of an improved assessment. Speaking about that, the titles in this conference are really long.
Yeah, sorry about that. So yeah, thank you for the introduction, and thank you to the organizers for this opportunity to talk about this work. So yeah, I did this work with my PhD supervisor, Rich Kerswell, and we're really excited about this. We heard a few talks in this workshop about, how mean profile, about some methods where mean profile is really the key. And this work really takes it to the opposite direction, where we want to find a condition or a rule which helps us to determine that mean profile or even higher order statistics. And we're going to use statistical stability ideas today. So what do we mean by statistical stability in general? Well, famously, turbulence reproduces the same flow statistics when we repeat the same experimental or numerical setup, even if we change the initial conditions slightly. And in a more formal language, we can say that turbulent attractor is a stable fixed point. So when we say that turbulence is statistically stable, what we mean is that if we perturb the statistics of the fully developed turbulent state, then those perturbations decay within statistical equations. Now, it's really difficult to capture that type of stability in the physical or Navier-Stokes framework, where we work with physical velocity fields, which are highly time dependent and really depend on the initial conditions we choose. And we might have a perturbation that grows along the turbulent trajectory, but doesn't affect the flow statistics. So even if the perturbation never decays, the system is still statistically stable. So if we really want to understand what drives and creates flow statistics, mean velocity profiles, or higher order statistics, then using the statistical framework is really the natural way to approach turbulence. And the first person to suggest that was Malkus, who in 1956 suggested that under certain assumptions, turbulent mean profile should be statistically marginally stable. Now, he had to make some approximations along the way, but basically what he suggested was solving Orr-Sommerfeld equation around turbulent mean profile. Now, his theory was later rejected by Reynolds and Tiedemann, but the method really took off. Many people were using it in different flow configurations usually to post-rationalize the appearance of large coherent structures. And the method worked in most cases, but not in all. And so it would be really nice to have an improvement. On another hand, with increasing computational power, nowadays more and more people are interested in statistical equations, cumulant expansions, different truncations to those equations. And again, these methods were applied in many different areas in fluid dynamics. So what we want to achieve with our work, we want to build upon the original Malkus's statistical stability ideas and use the statistical framework to extend the classical Orr-Sommerfeld analysis to include not only the mean velocity profile, but also second order statistics. And so the plan for today's talk is as follows. We're going to explore the stability both in the physical and statistical spaces. We're then going to develop our extended Orr-Sommerfeld analysis, and we are going to be using the channel flow to illustrate our work. And so that we are all familiar with the notation, let's quickly go through the definition of our channel flow setup. So we have non-dimensional Navier-Stokes equations with time-dependent pressure gradient G. So we keep volume flux constant. And we define our Reynolds number based on the laminar centerline velocity U, C star, channel half height H star, and fluid viscosity nu star. And so our channel domain is as follows. So we have non-slip walls located at y equals plus and minus 1. We have periodicity in the streamwise x and spanwise z directions, which then sets the fundamental wave numbers alpha and beta. And because we're going to be talking about statistics, we need an averaging procedure, and we're going to use the overline operator to denote the streamwise and spanwise averaging. And once we have this averaging procedure, we can now decompose our flow into the mean velocity component. So we will use capital U, and the fluctuation part, which is U tilde, which is the difference between the full flow and the mean velocity profile. So now that we have this definition of the system, let's start exploring the stability of the system. And we will start by recapping what the standard approach in the physical space is. So here in the diagram, at the very top of the physical space, we have fully nonlinear Navier-Stokes equations. And once we have decomposed our flow, we have two equations, one for the evolution of the mean velocity profile and one for the evolution of the base flow fluctuations. And you can see that basically we have all of the nonlinearity in these equations, so nonlinear interactions in the fluctuation equations, as well as the nonlinear term in the mean velocity equation. So now the standard approach to the stability makes significant simplifications. And in particular, we have a time-independent base state, which is just the mean velocity profile. And we ignore all of the base flow fluctuations. And we perturb only the fluctuation part of the flow and not the mean velocity profile. And when we make this ansatz, our Navier-Stokes equation simplified to the famous Orr-Sommerfeld equation around the turbulent mean profile, which is steady. And you can see that we have ignored all of the information about the base flow fluctuation field. So what we want to do, we want to improve this model by adding second order statistics. So we move to the statistical space. And the key point about moving to the statistical space, as I said in the introduction, is that in the statistical space, turbulence has stable, steady statistics. So we can take the mean velocity profile and second order correlation functions to be as our steady base state. And because we are only taking one step forward to include second order statistics, we are going to be using the CE2 cumulant expansion. So that's the cumulant expansion where we have first and second order cumulants involved, but we neglect all the cumulants of higher orders. And in the statistical space, we change our variables from the physical variables. So the mean velocity profile in the physical space remains the mean velocity profile in the statistical space. But we need to change our fluctuating field to the 2-point correlation matrices, which are defined as the average of the outer product of the fluctuation fields. And if we decompose our fluctuation field in terms of streamwise and spanwise Fourier modes, we can also use this expression to simplify the correlation matrices and decompose them in terms of different wave number modes, which then simplify to give only the product of the different Fourier modes of the fluctuation field. So I also want to emphasize that we don't use CE2 equations to generate our turbulent states. We only use CE2 equations to pose our spectral stability problem. So we still have fully developed turbulent state, and we only use this as a framework to study its stability. Now, to derive the equations in the statistical space, we can use the quasilinear or QL approximation in the physical space. And what's special about quasilinear approximation is if we look at the Navier-Stokes equations, we are neglecting the nonlinear fluctuation terms in the evolution equation for the fluctuation field, but we still maintain the nonlinear term in the equation for the mean. And now this term can be very easily transformed to the statistical space. And we can do about a page of algebra, and we can show that the equations in the CE2 space can be written as this. And in particular, this nonlinear term in the mean velocity equation can be written in terms of the correlation matrices. And you can see that all of the correlation matrices are coupled through the summation sign. So if we wanted to solve this stability problem, we would need to simultaneously solve for the evolution equations for each of the correlation matrices as well, for each of the wave number, together with the equations that impose incompressibility in the physical space. So it's great because in the statistical space, we have steady base state, so we could create our stability problem, pose it as an eigenvalue calculation, and that would be it. We would know the statistical stability of the state. But in practice, this is a very, very big problem to solve because instead of dealing with vectors, we're dealing with matrices. So the size of the calculation scales as the resolution squared. So wouldn't it be so good if we could move from here back to the physical space and still have the steady base state that we got from the statistical space? And you might ask, well, why can't we do that from the quasilinear system? Well, that's because in the quasilinear system, base flow fluctuations are time dependent. And if we tried to time average them, we would get 0. So we really need to find another way to do that. And this is exactly why we came up with extended Orr-Sommerfeld stability analysis. And this is what we propose to do. So as I already explained, we take the steady base flow statistics. And because we are working with finite channel, we will need to time average to improve the estimate of the steady statistics. And the instantaneous correlation matrices are rank 1 because it's just an outer product of the same vector. But as soon as we time average, those correlation matrices get higher and higher ranks. But it's not a problem. We can still approximate the correlation matrix as rank 1 by finding its leading singular vector, u tilde 0 mn. So we do that for each wave number. And now we're going to use this leading singular vector as a vector that represents the base flow fluctuations in the physical space. So we moved to this part of the diagram where we have now acquired a steady state. I wrote it in inverted commas because they don't really satisfy any equations. But it's something that represents the second order statistics back in the physical space. So once we've done that, we can revert the equations back from the statistical equations to the physical equations. And we further extend the model to allow perturbations not only to the fluctuation field, but also to the mean velocity profile. And remember that if we took the standard Orr-Sommerfeld approach, then the perturbations would be allowed only on the fluctuation part. So this is what the equations actually look like. So we have gained an extra equation, which is the equation for the mean velocity profile. And we have the coupling between different wave numbers, which involve interactions between our representative base flow fluctuation field that we got through leading singular vector. And we also have to solve these two equations for each of the wave numbers. And you can see that those light blue terms represent the original Orr-Sommerfeld equations. And we have two extra terms that couple the mean velocity perturbation with the base flow fluctuation representation vector. So we have reduced the size of the problem that we need to solve, because instead of having matrices, we now just have physical vectors. But we still have quite a big size because we're still coupling different streamwise and spanwise wave numbers. So for any reasonably sized system, this still might not be a very quick calculation to do. And we thought, why don't we go a step forward and create the minimal extended Orr-Sommerfeld analysis? And we thought we can just decouple all of the different wave numbers, which is equivalent to getting rid of the summation sign. And then we basically solve these three equations separately for each wave number. And in this case, the size of this problem is barely bigger than the standard Orr-Sommerfeld approach, because in addition of solving for the fluctuation field, we only have an extra variable, delta capital U, the mean velocity perturbation. So the cost of this eigenvalue calculation is not much bigger than the standard Orr-Sommerfeld approach. And of course, there is some computational cost in actually time averaging your correlation matrices and finding the leading singular vector, but at least this now becomes a calculation that we can do quickly without much waiting time. So that basically concludes the model development part. So just to recap, if we have a turbulent state in the physical space and we move it to the statistical space, we know that it has steady base state statistics. So if we consider the system at the second order cumulant level, we can then time average the base flow statistics, do the singular value decomposition to find the leading singular vector. That allows us to have this steady state with physical parameters instead of the correlation matrices. And so we can revert our equations back to the physical space to have the extended Orr-Sommerfeld equations, and as well as the minimal version where we decouple different streamwise and spanwise wave numbers. So now let's see how this method actually performs in practice. And for the application part, we chose to test our model with two-dimensional channel. Now we did that because 2D channel requires us to store only the streamwise wave numbers. So we reduce the computational size and we could test the model in more different ways and much quicker. Now we generate statistically stable and steady turbulent states using DNS via open source code Daedalus. And for this work, we fixed Reynolds number at 36.3 thousand. And today I'm going to focus on only two test states that we generated in 2D channel. So those are states F1 and F2. And we generated these states using body forcing F, which basically centralizes the pressure gradient to the middle of the channel. And why we're using body forcing? Well, we want to really diversify our test states, so we have different mean profiles and different levels of base flow fluctuations. And here in the diagram, you can see the mean profiles compared to the lambda profile, as well as the streamwise RMS velocities. So let's have a look how the models perform in statistical stability classification. So we can compare the eigenvalues for the different models. And here we're showing the eigenvalues for the standard Orr-Sommerfeld calculation using dots, extended Orr-Sommerfeld calculation using diamonds, and minimal extended Orr-Sommerfeld calculation using circles. And we're showing the leading eigenvalues for the first three streamwise wave numbers, m equals 1, 2, and 3. And all the eigenvalues above the dashed line are unstable. Now remember, we are dealing with statistically stable turbulent states. So if our models are good at classifying statistical stability, we would expect all the eigenvalues to be stable. And if we look at the state F1, we see that there is one unstable eigenvalue that was calculated with standard OS calculation. But this eigenvalue is then stabilized when we used our extended approaches. So we have an improvement in statistical stability classification. And what's most important is that that improvement is captured by the minimal extended model. So even when we decouple the wave numbers, we can get this improvement. And it doesn't really matter if the eigenvalues don't match completely. Now, the story is slightly different for the state of 2. So again, we see that for the eigenvalue that's unstable, which corresponds to m equals 2, we see again stabilization. So we see some improvement. There are two further unstable eigenvalues that correspond to m equals 1 and m equals 3 that don't seem to move at all when we use the extended models. So we see an improvement, but the improvement is only partial. And what I want to do for the rest of the talk is to discuss why, in this case, we see only partial improvement and where the limitations of our models are. So our model, of course, is only as good as the assumptions that we made when we created the model. So we had to approximate our correlation matrix as rank 1 when we calculated the leading singular vector in order to find a vector that represents the second order statistics back in the physical space. Before that, we had to time average our statistics in order to improve the estimate of the steady state. And even before that, we neglected higher order statistics when we chose the second order cumulant expansion CE2 to do the stability calculation in. So we're going to go through these and see whether or not they might be the limiting factor of our models. So let's start with a rank 1 approximation of the correlation matrix. So we're looking again at the state F2, where we have seen partial improvement in statistical stability classification. And here we have the singular values of the correlation matrices for the streamwise wave numbers M1, M equals 2, and M equals 3. Now for M equals 2, where we saw stabilization of the eigenvalue, we see that there is a massive gap of almost 2 orders of magnitude between the leading singular value and the next singular value. So our approximation is valid in this case. But you can see that for m equals 1 and m equals 3 cases where the eigenvalues don't move at all, the gap is much, much smaller. So perhaps this approximation is not as valid in those 2 cases. And perhaps our taking the leading singular vector doesn't really represent the base flow fluctuations accurately, and we're missing some sort of important features of them. And we thought, okay, maybe we can make this better, and maybe we can redefine our definition of the base flow fluctuation representation vector to include not only one, but several leading singular vectors. And we tried it with 1, 2, and 5 singular vectors, but we only saw an improvement of about 1% in the eigenvalue change. So you can imagine that really didn't make a difference in terms of statistical stability classification. So finding a robust way to represent second-order statistics back in the physical space remains a challenge of this model. Now, let's briefly discuss the time averaging of the base flow and neglecting higher order statistics effect on the model. And to do that, we designed the following numerical experiment. So we take a time-dependent base flow, which we have found by time-stepping full Navier-Stokes equations. We then add random perturbations to this base flow, and we first time-step those perturbations using linearized quasilinear equations. So now the perturbations feel time-dependent base flow, but the order of statistics that the perturbations experience is still limited at the CE2 level, because the quasilinear and CE2 systems are equivalent. So we really are testing the time averaging of the base flow effect. And then we take the same random perturbations and we time step them using full Navier-Stokes equations. So we are putting back all of the higher order statistics into the model. And we then look whether the perturbations grow or decay, and by averaging the energy over multiple runs. So here is the summary of the results. So when we use the linearized quasilinear model, we don't see perturbation stability. So perturbations are still growing. So that really tells us that time averaging of our statistics is not a limiting factor in the model. But when we use full Navier-Stokes equations to time step the perturbations stabilize. So we see the statistics of the new flow approach the statistics of the base flow. So that means, of course, as we would expect, if we have higher order statistics in our model, the system retains its statistical stability. And so with that, I would like to conclude my talk. So this is a brief summary of what we've discussed. So we have extended the standard Orr-Sommerfeld stability calculation to have not only the first order mean velocity profile statistics, but also second order statistics, which is the correlation matrix between the fluctuation fields. And we also extended the model by including the perturbation to the mean velocity profile. We have seen that in terms of statistical stability classification, that if the extended model has a different prediction to the standard model, then the extended model always has a change towards statistical stability. And that change towards statistical stability is captured by using the minimal extended model, which decouples different streamwise and spanwise wave numbers. And we have also discussed possible limitations of this work when we might observe only partial improvement in statistical stability classification. And that could be the representation of base flow fluctuations using singular value decomposition and leading singular vector, as well as neglecting higher order statistics if that doesn't work. And yeah, with that, I would like to thank you for listening. And if you want to find more details, there is a link to our preprint archive, and please don't hesitate to get in touch. And yeah, I'm happy to take any questions.
So my basic question is, if you reduce the Reynolds number, are you going to go towards better, obedience to your assumptions? And in particular, can you get the subcritical transition like Reynolds below 5772?
Well, we actually haven't tried going to much lower Reynolds numbers because we wanted fully developed turbulent states, and in 2D, the transition to turbulence happens at quite high Reynolds numbers. So we haven't tested that, but it's something to look at.
Martin?
Yeah, Vilda, very nice work indeed. I'm just speculating, looking at your equations, and my understanding was from your talk that you were missing some of the higher correlations somehow. What you probably, yeah, I mean, looking at the work what we did and on this what we call the statistical symmetries, which are very much nicely supported by our DNS and other DNS, probably these kind of things are missing here. I'm just speculating, and well, we might discuss that later. What you might do, because we also developed a modeling approach how to use the statistical symmetries or general symmetries to derive models. And they're probably coming close to what you have actually, but there's probably tiny little pieces missing. I'm speculating.
Okay, yeah, that would be very interesting to discuss. I guess one thing I would like to notice, the problem we reach is if we try to include higher order statistics to our model, it would be very difficult to map it back to the physical space in a consistent way. Because if you have second and third order cumulant, how do you find a physical vector that is consistent with both of those cumulants? So that's the problem we reached.
Okay, any other question? I'm curious. I mean, what is the relation between your equations and, I mean, you know the word by Farrell and I mean, are they related?
So I guess the main difference is here we're not trying to use the statistical equations to simulate turbulence and see how well we can capture it. We are just trying to use this as a framework to study the stability, if that makes sense.
I mean, I think that Farrell originally wanted just to find the streaks in Jupiter, basically. That's what he wanted.
Potentially. Rich, do you have anything to add to this?
Wait.
So Brian Farrell used the quasi-linear equations with forcing.
Ah.
So random forcing, and then he looked at the CE2 equations too. So there the idea is you're trying to use those to model the solution. What we're doing here is basically using the spectral problem of the statistical equations to study the stability. So we're not claiming that the Navier-Stokes equations is a solution of the CE2 equations. That's the key difference.
Okay, thank you. So if there is no other question, let's thank Bill. Oh, yeah, there is one. Wait.
Just a very, there was a point when you said you were going to eliminate the sum.
Yes, yeah.
Yeah, now, but were you eliminating everything, not just the sum, that whole term, right?
Oh, no, so
No.
just the summation. So yeah, we kind of solve these three equations separately for each wave number. So it becomes almost like Orr-Sommerfeld analysis, which you do for each of the wave numbers separately.
Okay, so you keep those UMN, V0, all
Yes.
that.
Yeah,
in
so
there.
we have the feedback from the base flow fluctuation perturbation back to the mean velocity perturbation, but for each wave number separately.
How can you have an MN on the really very basic? How can you have an MN on the right side and no MNs on the left sides of the that upper equation?
Because you also solve this equation at the same time. So you have delta capital U here, delta U tilde.
Oh, so that
and-
delta big U gets itself an MN index too? No. All right.
No, but yeah, let's talk over coffee.
Okay, I think that now we can really thank the speaker again. My 3 minutes, so I guess that we come back. So we come back at 11. We come back at 11:30.